Da da dun 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 dun.
Dun 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 dun.
Da da dun 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 dun
Dun
dun.
dun 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 dun.
Da da dun dun dun.
Dun 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 dun.
Da da dun dun dun.
Dun 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 dun. Welcome to dueling problem solving. Dun dun dun.
Welcome back, everybody. So previously, we learned how to do the sum of the numbers from 1 to n for any number n.
And we've found the sum of the numbers from 2 to 2n.
Which is the same as the sum of the even numbers. So today what we're going to do is we're going to go ahead and finish up the trifecta, and we're going to learn how to solve the sum of the odd numbers. So the specific problem that we want to solve today is we want to know what is the sum of the odd numbers from 1 to 49. But we're going to do something a little bit special today. We're going to play a little game called
Dueling problem solving.
So how this is going to work is Kyle's going to start it off, and he's going to solve this problem with any method that he can think of. And once he solves that problem, then it's my turn. I get to solve the problem with a different method that I can think of. And we're going to keep going like that. And
until one person cannot come up with a solution to the problem.
Yep, so the last guy to be able to solve the problem correctly with a unique solution wins the game. So we're going to let Kyle go ahead and get it started here. So Kyle, what method are you going to use?
Well, I'm going to use brute force, and about 30 minutes before we started this episode, I summed up all the numbers, and I got 625. I hope that's right because it took me 6 to 7 minutes and I almost fell asleep at the end of it.
All right, so Kyle's going to use the most straightforward method, but often not the most convenient method to do it. So he's going to use brute force. He's just going to add them all up. And so as long as the sum of the numbers isn't too large, sometimes you can get away with that. So if we were going to solve the problems from some of the odd numbers from 1 to 1,000,001, brute force wouldn't be an option for us. But in this case, there's not that many numbers, so he's able to do the brute force method and solve it. So hopefully you didn't make a mistake. Brute force, that's one of the drawbacks, is you spend so much time in computation that you run a good chance of making a mistake. So we want to see if we can exploit the structure of the problem in order to come up with a more efficient solution.
I really hope I got it right.
Me too. So now it's my turn. And so what I'm going to do is I'm going to use my favorite problem solving method is I'm going to solve a simpler problem. Simpler but related problem, and look for a pattern. So I'm just going to start off with the sum of the odd numbers from 1 to 1. How about that?
Okay.
So the sum of the odd numbers from 1 to 1 is just 1.
Mm-hmm.
Now do the sum of the odd numbers from 1
to 3.
to 3. I'll do 1 plus 3, and I'm going to get 4.
Okay.
Now I'm going to do 1 plus 3 plus 5.
And that's going to give you
9. Now let's do the next one.
1 plus 3 plus 5 plus 7.
That's going to give me 16. Now I'm starting to notice something here.
Yeah.
I'm starting to notice a pattern. So the pattern that I see is all the numbers on the right side here are perfect squares.
Mm-hmm.
And they're actually perfect squares of the number of terms that I have. So the first one, I have 1 term, and 1 squared is 1. The second one, I have 2 terms, and 2 squared is 4. Third one, I have 3 terms, 3 squared is 9, and the fourth one, I have 4 terms, and 4 squared is 16. So if my pattern's right, like I think it is, when I do the next one, I'm going to have 5 terms, and I should get 25. So let's try it out. So let me see, 9 plus 7 is 16, plus 5 is 21, plus 3 is 24, plus 1 is 25. So indeed it does work. So it looks like that I'm going to get the sum of the odd numbers from 1 to some number is just the square of the number of terms that I'm adding up, right?
That seems like the case.
Seems like the case. So I'm going to use that now for the problem that I have. But now I have a little bit of a problem because I don't know how many terms are
Because
in that sum.
usually when we did the sum of 1 to n, that went up by 1, so we could easily figure out that that was the number of terms, but now we don't have that easily, so
Yeah,
it's going to be a little bit of a problem.
These ones aren't going up by ones anymore, so I'm actually skipping by twos, and I'm going all the way up to 49, so I'm not exactly sure how many terms that I have. So, you got any ideas for me? Gonna help me out a little bit? Give me a little bit of assistance?
Well, maybe somehow you could turn this into a sum from 1 to a number.
Ooh, yeah, so if I could transform the number of numbers that I have here and do a one-to-one correspondence with some sum that goes from 1 to n and only goes up by ones, then that would tell me how many terms I have, right?
Yep.
Because I know if I say I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I know I have 10 terms there, right? And that would be easy. So one thing that I notice is these are all going up by twos, right? So let's just add 1 to every number in our sequence. Okay, now remember, we don't want to take the sum of this now. I'm just using this to try to transform what I've got into some different sequence that goes from 1 to n, only to be able to tell how many terms that I have, right?
Because if you just suddenly change the problem, that's going to give you a different sum.
Yeah, so we're changing the problem, but we're only doing it to find out how many terms that we actually have in this problem.
Because you would never add this up because you're turning it into a different problem.
All right, so when I do that transformation, I come up with this here. So I've got now 2 plus 4 plus 6 all the way to 48 to 50, but that's still not a sum of terms from 1 to n going up by ones, right?
Mm-hmm.
So what do I need to do?
Maybe you could change it a little bit more.
Okay. How about if I divided every number by 2?
That might be smart.
Yeah, because now what I've done is I've transformed it into something that starts from how much the terms are going up by, but it's still going up by 2. So if I divide it by 2, then those terms will only go up by 1. So let's divide every term by 2 here. So that's going to give me 1 plus 2 plus 3 all the way to 24, 25. Now remember, this is not the same sum as what I've got over here, but it does exactly correspond to the sequence that I have 1 to 1, right? Every number in here corresponds to a number that I have in my original sequence up here.
Yep.
Right? And so I know from that now that I have 25 terms. And so this is a general procedure you can use for any arithmetic sequence. So you figure out, you figure out how much it's going up by, and then you add or subtract a number to every single number that you have to make the first term equal to how much it's going up by. And then you just divide everything by how much it's going up by. That's going to leave you with a sum of numbers from 1 to n going up by ones that exactly correspond to the original sum that you have, and it will tell you, the last number here will tell you exactly how many terms you have. So if my pattern is going to hold up, I've got 25 terms. We said over here from our pattern, it should be 25 squared. So 25 squared, we know that from our shortcut for squares ending in 5, that this is going to end in 25, and the leading term is going to be this term times the next highest integer, or 2 times 3,
which is 6.
So that's 625. So lo and behold, Kyle and I solved this problem in 2 different ways, and we got the same answer.
So that might lead to something.
So that's a pretty good sign, right? That we're on the right track. So we've got 2 different solutions now. So I've got my solution, so now the ball's back in Kyle's court. He's got to come up with something original now to solve this one.
Okay. What if we made a geometric proof?
All right, so Kyle's going to try to do a geometric proof. I always like the geometric solutions because they're very visual, and my brain processes visual images a lot better than all those numbers sometimes. So we're going to do a little geometric proof.
So we switch over to GeoGebra, and we're going to use a geometric proof. So we're going to solve a little simpler but related problem in this, and we're going to find the sum of the odd numbers with 6 terms. So we have a square here that's a 6 by 6, and the area is 36. So now we're going to count how much squares in there. So first we start with 1 square, and then we move on to more squares. So we're going to add 3 more squares to cover around the 1 square.
Yeah, so you're just going to do it layer by layer and just add a new layer each time, right?
Mm-hmm. So then let's add 1 more layer around that. So that gives us extra 5 squares.
So now you have 1 plus 3 plus 5, and that's going to equal 9, which is the area of the 3 by 3 square that you have with your layers, right?
Now let's add another layer. So that's going to add 7 more. So I think we have a pattern here because it adds 2. So if we slide one of the 3 squares down.
Yep, so if you see this top layer, it exactly covers up the previous layer that we had. And then we've got 2 more here that cover up, but we always have to add these 2 additional squares, right? So every new layer that we add adds 2 more squares from the previous layer, which is the next odd term that we need in our sum, right?
So
the area is always going to be the area of the square, which is the sides of the square, which actually turns out to be the number of terms that you have, right? So it'll be the number of the terms squared.
So the next term should add 9 and should have an area of 25.
Yep, so let's just add those up just to show that. Okay. So 9 plus 7 is 16, plus 5 is 21, plus 3 is 24, plus 1 is 25. And we have a 5 by 5 square with our colors here. And so the area is 25 squared.
And the next one should have 11 squares, giving us a sum of 36, which is the area of the 6 by 6 square. And so that gives us 6 terms, and if we square that, it's 36, which is the area of the square. So if we use the 25 terms that we have, that should be 25 squared, which is 625.
Yeah, so we can keep just proceeding in this way by adding more and more terms. So if we went ahead and added 25 layers, we'd have a 25 by 25 square, right?
Which is 625.
And it would be the sum of the odd numbers for
1 to
25 terms, right?
Yep.
Or 1 to 49 with the odd numbers.
So now we tried 3 different solutions and we got the same number.
Okay, so what Kyle was able to show is that using his layers, and he would end up with 25 layers or 25 terms, that he would end up with a 25 by 25 square, and the area of that square would be 25 squared,
which is 625.
625, as we've shown previously. So this is Kyle's latest solution.
And so now you have to come up with another solution, maybe.
Yep, so now the ball's back in my court. So what I want to do this time, take our 4th solution, is I'm going to use all that work that we did in the previous videos to be able to solve the problem. So what I'm going to do is I'm going to take the sum of the numbers from 1 to 50, going up by ones,
okay,
and I'm going to subtract out the sum of the even numbers from 2 to 50, where n is the even numbers, and that will leave me with only the odd numbers from 1 to 49 of n, where n is just the odd numbers, right? See how that works? I'll take all of the numbers and then just subtract out the even ones, and that has to just leave the odd ones, right? So let's go ahead and do that. So what is the sum of the numbers from 1 to 50. So I'm just going to use the formula that we got from developing Gauss's trick. So that's going to be 50 times 51 over 2, or I can simplify that by canceling out the 50 and the 2, cancel out a common 2 from those. And that'll leave me with 25 times 51, which I'll rewrite as 25 times 50 plus 1 and use the distributive. So 25 times 50, so I'll temporarily drop the 0 and just do 25 times 5, which is 125. Add the 0 back in, so that's 1250 for the first term. The second term is 25, so that's going to be 1275. Okay, and then for the even numbers, so now I've got the sum of the numbers from 2 to 50 that I want to do, but I'm going to factor out the 2. So I'll have 2 times, and that'll leave me with the sum of the numbers from 1 to 25. You can see if I multiply the 2 back in, I'll get the even numbers from 2 to 50, which is what I want. Okay, and then I'll just apply the formula that we had again to the sum of the numbers from 1 to 25. So that's going to be 25 times 26 divided by 2, or 25 times 13. And I'll rewrite that as 25 times 10 plus 3, and that's equal to 250 plus 75 equals 2 times 325 equals 650. So now I can just go ahead and do that subtraction. So I'll take 1275 minus 650. So remember, the 1275 is the sum of the numbers from 1 to 50. The 650 is the sum of the even numbers from 2 to 50. And when I subtract them out, I'll get the sum of the odd numbers. And lo and behold, I get 625.
So now we did 4 different solutions and we got the same number, so I'm pretty sure that 625 is the right answer.
Starting to get really confident in our 625.
Yes.
All right, so now the ball is back in Kyle's court. Let's see if he can come up with anything. Looks like he's struggling over there.
Ooh, wait. Let's see if we can use Gauss's trick.
Ooh, all right. So we'll just do a little Gauss's trick. So what do you want to do?
So we're going to write the sum.
Write the sum. Okay, got it.
And then we're going to write it completely backwards.
I'm going to write it backwards. So just like we learned when we solved the problem of the sum of the numbers from 1 to n. Okay.
So now let's sum them all up.
All right, I get 50. 50. Whoa.
So now
Looks like I get 50 every single time. So that's interesting. Let's stop and think about that for a second, because when we did Gauss's trick before, we found out when we wrote it forward, we wrote it backwards, we got the same sum every time, which was pretty amazing, and that was for the sum of the numbers from 1 to n. But we note now that the fact that it went up by 1 each time was not the key structure in that problem that allows us to do this, right?
Nope.
The key structure in the problem that allows us to do this is the fact that it goes up and it goes down by the same amount each time, right?
Mm-hmm.
Doesn't have to go up and down by 1. It can go up and down by anything as long as it stays constant or is an arithmetic series, right?
So if it goes up by 5 every time, you can use Gauss's trick. If it goes up by 100 every time, you can use Gauss's trick. If it goes up by n every time, you can use Gauss's trick.
That's right. And in fact, when we get to arithmetic sequences and series later in this problem-solving series, that's exactly what we'll do in order to prove how to sum up any arithmetic sequence.
So Gauss's trick is really helpful.
Yeah. All right, so let's keep going. So now you got a bunch of 50 summed up.
And we figured out before that we have 25 terms.
Yep, so you're going to have 25 of these 50s.
That's going to be 50 times
So that's
25.
50.
Divide by 2.
Yep, so you got 2 sums now, so you got to go ahead and divide that by 2, right?
So now we can simplify the 50 and the 2, so that's going to be 25 times 25.
Which will be 25 squared.
Which is
We've
625.
seen that one before, so that gives us 625.
Yeah, I think 625 might be the right answer.
Yep, so the 5th solution is now in. And so the ball is now back in my court. Okay, so for the 6th solution, I'm going to try to take advantage of some of what we learned up here before. So actually, if I combine the first and the last term, which I kind of got from writing this forwards and writing this backwards, that'll add up to be 50, right?
Yep.
And it'll add up to be 50 every time. But if I take the average of the first and the last term, or any of these consecutive sequence of terms, if I take their average, I'll get 25, right?
Yep.
So I can actually transform my sum. What I'm going to do for the first term is I'm going to add 24, and that's going to give me 25. And for the very last term, I'm going to subtract 24, and that's going to give me 25, right? And this, actually, I can make that transformation because I added and subtracted the same number, right? So as long as I add and subtract the same number, my sum remains the same, right? So now for the second pair of terms, this 3 and the 47, what I'm going to do is I'm going to add 22 to the 3 to get 25, and I'm going to subtract 22 from the 47 to get 25, right? And for the next term, I'm going to add 20, or the next pair of terms, the 5 and the 45, I'm going to add 20 to the 5 to get 25, and I'm going to subtract 20 from the 45 to get 25, and I'm going to keep doing this for every successive pair of terms. And the middle term in this sequence of numbers that I have here in this series is actually going to be 25, right? So I'm left with a whole string of 25s, right?
Yep.
And I know from figuring out how many terms there were that I've got 25 terms, so that is going to give me 25 squared equals, yeah, we're going to know what 25 squared is like the back of our hand. That's going to give me 625. So that's solution number 6. I was successful. Ball's back in Kyle's court now. He's starting to sweat now. He's feeling the pressure.
Okay.
We need solution number 7.
So the way you did that last problem, I noticed that there's a simpler way to do it. So the average of the terms is always going to be 25. So what we really need to do is find the average of the first and last terms.
Yeah, so that's a good point. So you notice from what I did here, I kept taking successive sequence of outer terms, like I did the 1 and the 49, the 3 and the 47, the 5 and the 45, and kept pairing them up like that, and the average was always 25, right?
So we could just take the average of the first and last numbers and multiply by how much numbers there are.
Ooh, that's a good idea. Since it's always 25, I don't need to waste time writing them out every time, right?
Nope.
So when I take the average of the first and the last terms, what do I get?
When you take the average of the first and last terms, that's going to be 25.
Yep, it's 1 plus 49 divided by 2.
It's 50 divided
25.
by...
So all of those pairs of successive terms will have that average, right?
So, since there's 25 terms, it's going to be 25 times 25, which is 25 squared, which is, as we all know, 625.
So that's even a really nice way to think about it. So as long as I've got the arithmetic sequence and they go up by the same amount each time, I take the average of the first and the last terms and I multiply it by the number of terms that I got, and I have the sum. And so the nice part about that is when we do the arithmetic sequences and sums later in this series, that's exactly the formula that we'll come up with for the sum of any arithmetic sequence. So it's the average of the first term and the last term times the number of terms you have. And so that's pretty simple. So we know a good way to figure out the number of terms now. Taking the average of the first number and the last number is pretty easy, right? So any sum that we have now that goes up by the same number, increases by the same number each time, we can use that method to solve, right? All right, so I guess the ball is back in my court again. So we're looking for solution number 8 now.
Can you figure out an 8th solution?
Well, let me think for a second here. Yeah, I got nothing. I'm out of ideas. I've
It
pretty
looks
much...
like that I am the winner.
Congratulations, Kyle. So Kyle managed to win the first inaugural dueling problem solving.
Well, Dad, maybe at some point in time you might win.
Yeah, if I keep practicing, maybe I'll be able to catch up with you. What do you think?
Maybe. Maybe not.
All right, but the point of this whole series here and why we went through this is when you're solving your problems, always try to think of as many solutions to the problem as you can, because you might be able to discover some structure in the problem that gives you a really easy solution and also extends to many other solutions. so that you can apply to different problems when you're trying to convert some problems to the problems you know how to solve. The more ways that you can solve a given problem, the better off you are. So when you're doing your problem solving, always try to think of different solutions, especially when they mix some algebra stuff with some combinatorics and geometry. When you can kind of understand a problem from all those angles, then you really understand the problem. So, but this isn't over yet. So we came up with 7 solutions. So we want you guys to participate in the game as well.
So if you can find any other solutions that we may have missed, please put them in the comments and we will look them over and see how you did it.
Yep, so the last guy to propose the final solution using a different method than anything that's been presented previously will be the final winner of the game. All right, so we're going to sign off for now. We hope you guys enjoyed this one, and we'll see you again next time.
Bye!